Welcome back. We're now on lecture 10 entitled Hypothesis Testing of Multiple Populations. So, we're now going to extend the concept of hypothesis testing to two populations. We're going to test matched pairs. We're going to also test independent populations. We're also going to we're also going to test hypothesis for proportions and as well as variances. So we have for population means we have dependent samples and independent samples. Then we're going to test population proportions and population variances. Okay, so this is similar to what we did when we constructed confidence intervals for multiple proportions. Okay, but in this case, we are testing hypothesis. So when we have dependent samples, these can be paired or matched samples. So we look for the difference in the paired samples. So we're actually interested if there's a difference between any two population means. And in this test, we assume that the populations from which the samples are coming from are normally distributed. So the test statistic is the t value, and the degrees of freedom are n minus 1. So this is the formula for how we're going to find the t value. So we first have to find the differences and the mean of the differences. Okay. Now, D note here is the hypothesized mean difference. Okay, so this is from the question. If there's a difference or there's no difference or whatever exists in the question. And SD here is the sample standard deviation of the differences, and the N is the sample size, that is number of pairs. So we can have a lower tail, an upper tail, or a two-tailed test, okay, where the T is just given by that formula. So the areas of rejection for a lower tail are the areas that are less than minus T alpha. For upper tail, the areas that are greater than T alpha. And for a two-tailed test, these are the areas of rejection. Let's have our example. We have that example. We're saying that assume you send your salespeople to a customer service training workshop. And then, has the training made a difference in the number of complaints? Okay? So we're saying, has the training made a difference in the number of complaints? That is the number of complaints before and the number of complaints after. So we take the differences and then find the mean difference, which is a minus 4.2. The standard deviation of the differences is 5.67. Okay, so our hypothesis, we're saying that is mu1 minus mu2 equal to 0. Okay, so this can also be written mu x is mu x equal to mu y. So you can write mu x minus mu1 equal to 0 or mu x equal to mu1 for the now hypothesis. Okay, So that's what we have. So here we're saying that the hypothesized difference is 0, okay, which is the one that we put there. Okay, so the null hypothesis is actually, so what we're saying here in our question, our alpha is 0.05. Our alpha is 0.05, our difference is minus 4.2. Okay, then the critical value at alpha equal to 0.05, at alpha equal to 0.05, that means that we divide our alpha into 2, that is 0.025. Okay, and we're looking for the critical values using the T table. So, and our degrees of freedom are 4. Okay, so at 4 and alpha equal to 0.025, this is the critical value, minus 2.776 and a positive 2.776. So this is our region in which we failed to reject H naught. So our test statistic, we get a difference, and the hypothesized difference is 0. We replace down there, and we're going to find that the t-value is minus 1.66, which falls in the area in which we failed to reject H naught. Therefore, the conclusion is that there is no significant change in the number of complaints. Okay, we now proceed to testing a hypothesis for a difference between two independent samples. So here we're saying that these samples are unrelated and are normally distributed. So we have two cases. If the population variances are known, we use the Z value as our test statistic. And if the population variances are unknown, we use the T distribution. So if the population variances are known, we use the Z distribution. If the population variances are unknown, we use the T distribution as our test statistic. Now, we now proceed to the first case when the population variances are known. Then we have that the variance of the two samples, which is x bar minus y bar, is just given by this formula, okay, and the z value is found by this formula. Okay, so that's how we find the z value. So then now hypothesis will be x, mu x minus mu y, okay, which is equal to the difference, and the test statistic is just the mu x minus, the test statistic for mu x minus mu 1 is given by this, is the z value, which is found using this formula. So we can have a lower tail, upper tail, or two-tailed test. Okay. That shows the rejection regions for a lower tail, for an upper tail, and a two-tailed test. Okay. Now, suppose the variances are unknown, we first assume that the variances are equal. Then we have the other case in which we assume that the unknown variances are unequal. So if the variances are equal, we use the pooled variance. Okay, and we use the t-value, and with the degrees of freedom nx plus ny minus 2. So that is the test statistic, and the SP there is the pooled variance, and that is the degrees of freedom. Okay, where n1 is just simply nx and n2 is ny. That shows the decision rules, the critical, the rejection, and the areas in which you fail to reject for the lower tail test, upper tail test, and the two-tailed test. Okay, now let's have an example. You are a financial analyst for a brokerage firm. Is there a difference in dividend yield between stock listed on the New York Stock Exchange and Lusaka Stock Exchange? You collect the following data. So we have the sample size for New York Stock Exchange is 21 and Lusaka Stock Exchange is 25. We have the means and the sample standard deviation. Assume both populations are approximately normal with equal variances. Is there a difference in the average yield at alpha equal to 0.05? So in this case, we're going to have a difference in the means and also the hypothesized difference, which is just a 0. We calculate the pooled variance in this manner, which is a 1.5021. Then when we replace in our formula, we find that the t-value is actually 2.040. Now, our null hypothesis is simply mu1 minus mu2 equals 0, which is that there is no difference. And the alternative hypothesis is the opposite, which we're just saying mu1 minus mu2 is not 0. So we find the critical values for t at those degrees of freedom. The degree of freedom is 44. Alpha is 0.05. So we go on our t table and we find that the values, the critical values are 2.0154. So these are the critical values. So they now help us identify the rejection regions. And the t-value is 2.040, which is greater than 2.0154. So it falls in the rejection region. Therefore, there's no evidence that there's a difference. Okay, so we are rejecting, the decision is to reject H naught. So if we are rejecting H naught, is that we are concluding that our decision will be to reject H naught, which just makes us conclude that there's no difference in the means. Okay. We now look at the case when the population variances are unequal. In that case, we're going to use the t-value as our test statistic with v degrees of freedom. So this is how we find the degrees of freedom. So in this case, we're not using the pooled variance. Okay, we're going to use the separate variances. Test statistic is still T. This is how we find the T value and the degrees of freedom. Okay, so the way to the decision rules are still similar for when using the pooled variance. So the decision rules when using lower or upper or two-tailed test are still similar. So the difference was just in the formula, which was highlighted. Now, apart from testing hypothesis for the means, we can also test hypothesis for two proportions. Okay, so in this case, we can have two proportions, px and py. So we want to know if there is a difference between the two proportions. Again, we assume here that np multiplied by 1 minus p is greater than 5. So we use the z value as our test statistic, and that is the formula for finding the z value. Okay. Okay, so this is the formula where P naught is just nx multiplied by P hat x, which is the sample population of the first sample. The sample, okay, so P hat naught is just the proportion obtained from this formula, which is the sample size of the first from the first population multiplied by the population proportion multiplied by the, so p hat is obtained from this formula, which is just the sample size of the first population multiplied by the sample proportion of the first population plus the sample size from the second population multiplied by the sample proportion of the second population divided by the sample size from the first population plus the sample size from the second population. So this is how we obtain the z value. There we describe the decision rules, the decision rules for upper tail, lower tail, and two-tailed test. We have our example there. Is there a significant difference between the proportion of men and proportion of women who will vote yes on proposition A? So in this example, we're told 36 of 72 men and 31 of 50 men indicated that they would vote yes for this proposition. Test at alpha equal to 0.05. So this is the hypothesis, is that the population, is there a difference? The now hypothesis says that there is no difference, that the two proportions are equal, and the alternative is the opposite, which just says that there is a difference. So we get the proportion, the sample proportions from the data that is given, then we estimate the overall proportion, which is just 0.549. We place in our formula and we find that the z-value is a minus 1.31, which when we compare to the critical values, this is false in the area in which we failed to reject. So when we fail to reject H naught, we are saying that there is not significant evidence of a difference between men and women in proportions who will vote yes for proposition A. Okay. After testing hypothesis for proportions, we now want to see how we can have a hypothesis test for true variance. Remember, sometimes we want to know if the variances, the unknown variances are equal or are not equal. We want to know whether we should use the pooled variance or the separate variances. So in that case, we can test the equality of the variances of two populations and make a decision of whether to use the pooled or the separate variances when testing for their means. Yeah. So when testing two population variances, we can again use a lower tail test, an upper tail test, or a two-tailed test. Okay. Now, to use when testing for two variances, we use the F statistic. Okay, so the F table was attached to your assignment too. So by now you have the F table. So that is the table that we're going to be using. Okay, so that is the random variable, the F random variable. Now in the F distribution, we have 2 degrees of freedom. We have the numerator degrees of freedom and the denominator degrees of freedom. So the numerator degrees of freedom is just obtained by nx minus 1, which is just the sample size of the first, from the first population. And the denominator degrees of freedom is obtained from ny, is given by ny minus 1, which is just ny is the sample size from the second population. So we denote f as in f has v1 comma v2 degrees of freedom. So the test statistic is the f, and the f is just obtained, the f value is obtained, is given by a ratio of the two sample variances, which is just S, the variance, the sample variance of the first population divided by the sample variance of the second, from the second population. Usually the numerator is the sample variance which is larger, and the denominator is the sample variance which is smaller. Okay, so decision rules also depends on whether you have a one-tailed or a two-tailed test. Okay. Now, if we have an upper tail test, then we're going to reject H naught if it's greater than the F value. So F value is just given, it's given by that f nx minus 1 comma nx ny minus 1 comma alpha. Okay, and if we have a two-tailed test, then we're going to divide the alpha by 2. Okay, so reject H naught if alpha is greater than that critical region. Okay. Let's have an example. Okay, so we have that example where we have the New York Stock Exchange and the Lusaka Stock Exchange. Okay, so is there a difference? Now we're testing the standard deviation, the variances. So is there a difference in the variance between the New York Stock Exchange and this value? Okay. Okay, so in the null hypothesis, we're saying there's no difference in the variance, and the alternative, we're saying there is a difference in the variance. So alpha was 0.05, was it? No, alpha is 0.1. So we divide that 0.1 by 2, 0.1. We have 0.05. Okay, so we find the value from our table. The numerator should be, degrees of freedom should be 24, and the alpha is 0.05. So that should give us that value. Okay, so that gives us the value. And so this is how we find the degrees of freedom. Okay, so that is how we find the critical value, which is 2.03. We now find our F value, which is just the ratio of the variance, the sample variances. So 1.30 divided by 1.62, which gives us a 1.256. Now, 1.256 falls in the region in which we fail to reject H naught. So our conclusion is that there is no sufficient evidence that there is a difference in the variances at alpha equal to 0.1. Okay, so we've come to the end of our lecture. So we have compared two dependent samples. We have also compared two independent samples, two proportions, and we have used the F table to find the difference between two population variances. Thank you.